Okay, so a blank logarithm has a base of 10. We call a base 10 log a common log. And a logarithm that has base of e is called a natural log. Okay, the inverse of an exponential function is a logarithmic function. And let's see, growth occurs when b is greater than 1 for y equals b to the x, and decay is what occurs when b is between 0 and 1, non-inclusive, for y equals b to the x. So b greater than 1, the base greater than 1 is exponential growth. The base between 0 and 1, non-inclusive, is exponential decay. Okay, the domain of an exponential function and the range of a logarithmic function, that's always the set of all real numbers, which is negative infinity to positive infinity. The parent graph of an exponential function has a horizontal asymptote that is along the x-axis. The parent graph of a logarithmic function that has a vertical asymptote which lies along the y-axis. Okay, the formula that calculates continuously compounded interest, that is A equals P E, Euler's constant, to the RT power, the PERT formula. A solution that is algebraically correct but does not check in the original problem, we call that extraneous. An extraneous solution. Okay, so in number 9, we want to sketch the graph of y equals 3 to the x plus 1 power minus 2. And we want to recall transformation form is whenever we have a constant a times then our base of the exponential, that's raised to the c times the quantity x minus h power plus a constant k, and that is transformation form. So we're going to use the equation that we're given to identify a, b, c, h, and k. So the a is the constant being multiplied times the base, and that's a 1 in this example. The b is the base of the exponential, and that's a 3. Then the c is the coefficient on the x in the exponent, which is a 1 in this example. H, the horizontal shift, is going to the left since it's a plus 1, so h is negative 1. And then k is the vertical translation. This is a minus 2 for the k, so we're going down 2. Okay, our anchor points are always, for an exponential parent graph, 0, 1, 1, comma, b, and then negative 1 and the reciprocal of b. So we're going to go through the point 0, 1, our b is 3, so 1, comma, 3, and then negative 1, 1/3. Okay, then to do any dilations, we're going to multiply the y value by the a, which is 1, and multiplying something by 1 doesn't change it, so we'll just go straight across here. Then horizontal translations occur by dividing the x by the c value, which our c is also 1, so there's been no dilations and no reflections. Okay, then horizontal translation, we add the h to the x, and our h is negative 1. So we're going to add negative 1 to each of the x values. So 0 plus negative 1 is negative 1, and the y stays the same. Then 1 plus negative 1 is 0, and the y stays the same. And then negative 1 plus negative 1 is negative 2, and our y stays the same. Okay, then our vertical translation, we add the k value to each of the y coordinates. So we're going to add negative 2, and the x's will all stay the same. Then we have a 1 plus negative 2 is negative 1. 3 plus negative 2 is positive 1. And 1/3 plus negative 2 is a negative 5/3. Okay, so our transformations, if we were asked to describe them for this equation, we went down 1, to the left 1 and down 2. So translated left 1 unit and down 2 units. Okay. And then we can go ahead and find the equation of our asymptote, which is having to do with the k. Since it's a horizontal asymptote, it would normally be for the parent graph along the y-axis, the x-axis. This one's been moved down 2 units to be at negative 2. Okay, then y equals negative 2 is the equation of the asymptote. The domain is all real numbers. The range, though, is bounded, half-bounded by the asymptote. So starting at negative 2 and then headed up to positive infinity. We're going to go through these anchor points at negative 1, negative 1, 0, positive 1, negative 2, and then negative 5/3. Okay, and then we need another additional point. So if we were to substitute, let's see, we have negative 2, negative 1, 0. So let's put in a 1 for the x, and then we'll put that into our equation here. So we'll have a 3 raised to the 1 plus 1 minus 2 would be 3 squared minus 2, which is 9 minus 2, which is 7. So the point 1, 7 is on the graph, and then we can use those guide points to sketch our exponential growth curve. So this would be an example of exponential growth, right? The slope starts out shallow, and then in this J-curve shape, it gets really, really steep, really, really fast, and that's exponential growth.